All right, welcome back. So today in this session we will talk about 2.3, that is spanning sets and linear independence. So this section is all about linear combinations of vectors. We have seen that we can view solving a system of linear equations as asking whether a certain vector is a linear combination of certain other vectors. We explored this idea in more detail in this section. It leads to some very important concepts which we will encounter repeatedly in later chapters. Anyway, guys, so far we have been solving a system of equations, and now we will see that actually what is the relationship between the linear combination of when we're actually solving the linear system. As you know, first we need to form the augmented matrix, right? If you notice that the first column, it will be the coefficients of x, let's say x1. The second column actually represents the coefficients of x sub 2 and blah, blah, blah. And you will see that they are just the linear combination of certain vectors. And when we ask a question, does a system has a solution or not, that means that that's a constant vector. Can it be written as a linear combination of, the column vectors of the augmented matrix? I mean, that's a coefficient matrix. Anyways, here we have to know actually that's the meaning of span. In dictionary, it is the full extent of something from end to end, or the amount of space that something covers. But here, when you talk about spanning, or a set of vectors spans a space, that means that a set of vectors, right? Here, if you're talking about a kind of space, actually every point is represented by a certain vector. That means that the space is filled by a bunch of vectors, maybe of course infinitely many vectors. All right. So let's actually start this section with this question. Is the vector 1, -7, 2? Let's say for now, this thing is, okay, is it recording? Good. Let's say this one is W, okay? A combination of the vectors, let's say this one is U and this one is V, right? So the question is the vector a linear combination of the vectors? Means, can we just write this W as the C1 times vector U plus C2 times vector V, that's equal to W, right? To do this one, as you know, what is it? We have here just a system of linear equations, right? We need to solve this. The question is the system consistent or not, right? To do this one, actually, you can just write as here. If I write the things, here we have C1 and vector U is -1, 2, -2. Actually, instead of writing this C1, C2, let me just write and the X and the Y. These are scalars and these are vectors, right? Here we have X plus Y times vector V. That is 1 minus 3 and 2. And on the right hand side, we have W. What is it? That is 1 minus 7, 2. Now we have already started actually about solving the system, right? To solve the system, as you see here, X is the variable. If you just write this as a system, here we have minus X plus Y is equal to 1. From here to X minus 3Y, that's equal to minus 7. The third equation, to minus 2X plus 2Y, that's equal to, what is it? It is 2. And to solve this one, as you know, first we need to form our augmented matrix. I can just write it as here, that is -1, 2, -1, -1, 2, sorry, -2. And here we have 1, -3, and 2. And here we have augmented column, that is 1, -7, and 2, right? So how can I do this? First, we need to reduce this, right? To reduce to echelon form or echelon form. So if you notice here, also here, the first column, right? What are these components? These are just the coefficients of this X, or that's our first vector. And how about the second column? That is just the coefficients of y, or that is our this vector. And how about the third one? It's just the w, this vector, right? So here we have first, if you add, okay, minus 1, 1, 1. If you add the second row to the third row, here we have 0, minus 3 plus 2, it is minus 1, minus 7 plus 2, it is minus 5. And multiply the first row by, multiply the first row by 2 and add to the second row. Negative 2 plus 2, it is 0. 2 plus minus 3, minus 1. 2 plus minus 7, it is minus 5. As here, the second and third row are the same. If I just multiply the second row by negative 1 and add to the third row, and after that also multiply the, adds the second row to the first row, what we got here? Here we have negative 1 and minus 1 plus 1, it is 0, minus 5 plus 1, minus 4. And here we have 0, 1, 5, here we have 0, 0, 0, right? And one more thing, because here it should be 1, multiply the first row by negative 1, here we have 1, 0, 4, 0, 1, 5, 0, 0, 0. So now that means that here that x is equal to 4 and the y is equal to 5. That means that our system is consistent, right? So that means that this w is a linear combination of u and v. I can just write it as 4 times vector u plus 5 times vector v. It gives us vector w, right? And see, there's the relationship between how the things are connected to each other. It's asking, is the vector a linear combination of these given vectors? It means now if you just form the system, is the system consistent or not? Now let's see another example. Is the vector a linear combination of the vectors? Now immediately you have some idea about this. We could just write our augmented matrix. That is the first column, right? It's 0, 3, 2, and 5, 0, 7. And here we have 2, 5, 11, right? So is the vector a linear combination of the vectors, the given vectors? That means that is this system, right? Right? Which is represented by this matrix, augmented matrix. Is it consistent or not? So to do this one, here we have 0, so it should be not here. So let me just interchange the first row with the third row. So here we'll have 2, 7, 11, 3, 0, 5. The first row comes here, 0, 5, 2. Okay, so now let's multiply the first row by 1 over 2. So we will have here 1, 7 over 2, 11 over 2. The second one by 1 over 3. So here we have 1, 0, 5 over 3. The third one, okay, for now, all right, let's just multiply by 1 over 5. Here we have 0, 1, 2 over 5. Right. So now if you multiply the first row by negative 1 and add to the second row, we will have here 1, 7 over 2, 11 over 2. And I can just write it as decimals, I think. Okay, here we have 3.5, 5.5, and here we have 0, and here we have minus 3.5, right? And here we have 5. Okay, we just multiply minus 5.5, so that is minus 5.5 plus 5 over 3. That is equal to, here we have minus 23 over 6. And here we have 0, 1, 2 over 5. Okay. So now what we have here, multiply. Okay, let me just interchange the second and third row here because here we have 1. Right. So I can write this one as 1, 3.5, and 5.5. And here we have 0, 1, 2 over 5, or that one is just 0.4, 0.4, and here we have 0 minus 3.5 and minus 23 over 6. Okay, so 1, 0, here we have 1, multiply the second row by 3.5 and add to the first row, so here we will have 0, 0 point, that is minus, we multiply by 3.5, 3.5 times, what is it, 0.4, and we just add 5.5, that's equal to, here we have 4.1, and here we have 0.4. And 0 multiplied by 3.5 and add to the third row is equal to 0, and 3.5 times 0.4, and the minus 23 is divided by 6, that's equal to minus 73 over 30. Okay. So now from here we can stop. As you see here, it's already actually in reduced form. It is 1 and it is 1. And how about the last row? If you look at here, right, and it is corresponding equation will be here 0 on the left hand side. On the right hand side we will have negative 73 over 30, and which is not possible. 0 is not equal to minus 73 over 30. That means that the given vector, let's say this one is W, this one is V1, this one is V2. W is not a linear combination of V1 and V2, because the given system, right, this one is not consistent. Okay, so what we have here, from here we can actually generalize this idea and give it as a theorem. Then a system of linear equations with augmented matrix. That's our augmented matrix. This A is coefficient matrix. This one, as you know, that a vector whose components are constant terms of the system is consistent if and only if. Here we are using again if and only if. You know what we mean by this. It has two-way implication, right? If B is a linear combination of the columns of A, right? So that means that, for example, if you just consider this example, how can I write this thing? You see, here we have x times, right, 3, 5 plus y times 2, negative 3, and on the right hand side we have 1, negative 11, right? So we are saying that if and only if this B, that is our B, is a linear combination of the columns of A. So that is A, right? The columns of A, 3, 5, the first column, 2, negative 3, the second column. So can we just write B as a linear combination of these two vectors? That means that can we find some suitable X and Y when I substitute here and multiply this vector by X, multiply the second vector by Y, and add them up, it gives us this vector. If it is so, that means that a system of linear equations with augmented is consistent. If it is consistent, that means that B can be written as a linear combination of the columns of A. All right. Next important thing, spanning sets that we actually talked about in the first slide, right? And linear independence. Definition. If S equals, what is it? S is a set of K vectors. Those are V1, V2, Vk. Here we are given a set. The set contains K vectors. And is a set of vectors in Rn. Each vector is taken from Rn. Then the set of all linear combinations of V1, V2, Vk is called the span of V1, V2, Vk. And it's denoted by span, this one, right? V1, V2, Vk. And what is this? We are saying that here the span of S, right, is all the linear combinations of these vectors, right? It gives us, what is it, some kind of another space. For example, you'll see that in this example, show that R2 is the span of these two vectors. Okay, what does it mean? It means that this R2, when we just say R2, we mean two-dimensional space. That's our coordinate system, right? Here we have Y, here we have X, and show that R2, that is R2, two-dimensional space, right? So R2 is just equal to span of this. That means that all the linear combinations of these two vectors. What are these? These are just, let's say, here we have C1, and here we have 2, -1, plus C2, and here we have -1, 2, right? So that means that if you just pick any vector here in two-dimensional space, let's say whose coordinates, let's say this one is W, and whose coordinates are, let's say, A and B. And I'm saying that any vector here can be represented as a linear combination of these two vectors, right? It means this. It can be this vector, it can be this vector. If it works for any vector, that means that actually every vector can be represented by a linear combination of these two vectors. That means that the span of these two vectors actually, what is it, is equal to R2. It means that it just fills this space. So again, this is C1, C2. Now, instead of the C1, C2, let me just write. Assume that we are given any vector, and here we have X, and here we have Y. These are linear combination of the first and the second vectors. And I'm claiming that if you just give me any vector from this R2, actually I can find such X and Y so that X times the first vector plus Y times the second vector, it gives us this AB. This AB is given, we know this vector. What's unknown here, is it possible to find X and Y? We are looking for X and Y. Now to do this, again, we know that first we need to write the augmented matrix, right? So here we have 2, -1, -1, and 2. Here we have A and B, right? So immediately if I just interchange and multiply the first column by -1, here we have 1, -2, -B, and second line will be 2, -1, A. And if you multiply the first row by -2 and add it to the second row, here we have 1, -2, -B. -2 plus 2 is equal to 0. And here we have -2 times -2, it is 4. 4 plus -1 is equal to 3. And here we have -2 times B, it is 2B. So here we have A plus 2B. Right? Now, let me just divide by 3. So here we have 1 minus 2 minus B. Here we have 0, 1, A plus 2B over 3. So now if you just multiply the second row by 2 and add it to the first row, here we have 0, 1, 0. Here we will have 0. Here we have 1. And here we have A plus 2B over 3, right? And I should multiply this by 2 and add it to the first row. That means that here we have 2A plus 4B minus 3B, right? Which is equal to 2A plus B. So here we will have 2A plus B over 3, right? And see here for every A and B, right? Actually, I can evaluate this. Even we don't have zero division here. For every A and B, if we just substitute here, we will get one value. So what is X then? That X will be 2A plus B over 3. And this Y will be A plus 2B, right? That is A plus 2B over 3. So that means that now if I substitute this value for X here, and this value Y from here, right, is always equal to this AB. That means that this, I mean, span of these two vectors, 2 and -1 and -1 and 2, span of this is equal to R2. It means that all the linear combinations of these two vectors, they fill this two-dimensional space. Okay, so this is what it means. So if we say that here span of S equals Rn, then S is called the spanning set for Rn. All right. Let's E sub 1 or just simply E1, E2, En be standard unit vectors in Rn. Then Rn is just equal to spanning sets. They serve as a spanning set for Rn. Right? Why is it so? Again, if you just pick any vector, right, from Rn. So what we have here, this X will be, from Rn means it has n components. So here we have x1, x2, dot, dot, dot. Here we have xn. And I can just write it as x1 times, what is it? 1, 0, 0, dot, dot, 0, plus x2 times, here we have 0, 1, 0, dot, dot, 0, dot, dot. And the last one, here we have x sub n, right? 0, 0, dot, dot. Here we have the last component is entry is 1. I can just write it as this. And what do you see here? The first one is just E1, right? Here we have E1 times, actually it's E1, X1 times E1. The second one is X2 times E2. Guys, again, don't get confused. This X1, X2, these are scalars. And E1, E2 is these vectors. If I just try to write in boldface, it's getting a bit messy. That's why I'm trying just to write this in simple form. Plus, and here we have X and here we have sub n, right? Any vector, as you see here, I can write it as a linear combination of this n vectors, which means that then this Rn is just equal to span of this unit vectors. Actually, we know that actually these are called standard unit vectors, right? Okay. Next, find the span of these two vectors, 1 to 0 and 3 to -1. No. Find the span of these two vectors. What does it mean? It means that what do actually these things represent, right? This span of these two vectors, if I just write here x times, here we have 1 to 0 plus y times 3 to -1. Okay. If you just span all of these vectors, what does it give us? That is a vector, and these two vectors, they are not parallel to each other because we can see that the scalar multiple, a multiple of this vector does not give us this vector. So these are in three-dimensional space. So it is something, let's say this one is x1, this one is x2, and this one is x3, right? 1 to 0, maybe this one is our first vector. Let's say this one is u, and the second vector is, let's say it is this vector. Let's say it is v. Okay. So that means that the question is, what do we get actually by linear combination of these vectors? If you just get all the linear combinations of these vectors, what do we get here? Actually, geometrically, we get a plane, right, that passes through the origin. Right? We get a plane. That's the first, actually, the answer to the first part of the question. What is the geometric description of the span of these two vectors? It is just a plane which passes through the origin, right? So that means that's, what is this? Okay, simple, just a plane. That's the geometric description of the span of these two vectors. And how about algebraically? I mean, algebraic means this span of these two vectors. Sorry. That's x plus y, s3y, 2x plus 2y, right? And here we have 0, -y. And what does it mean? And it means that if you're just saying that some kind of vector, let's say, is here, 1 to 0, plus here we have y, and the 3 to -1, right? So now, if we want to get the general equation of this plane, and at the time, we need to just do this algebraically, right? The second part is it says that find the span of these vectors geometrically and algebraically. So that thing is, since actually the span of all of these vectors, it gives us a plane that passes through the origin, right? it passes through the origin, then what we have here? Here we will have the equation of this plane. Let's say the plane equation of this plane will be a times x plus b times y plus c times z is equal to 0. It's a plane, and on the right hand side we have 0. That means it is passing through the origin, right? Now we know that actually every vector on this plane, right, it is just in the span of these two vectors. So that means that if I just substitute here, one vector here, it belongs to this, another vector here, it belongs to this, right? So that means that we need to just solve this equation. Here we have, let's say if you just substitute this vector, what we have here? Here we have a, right, plus 2b, and third component is 0. Here we have 0. And here we have 3a plus 2b minus c, right? That's equal to 0. Now from here, how do we actually determine the values of a and b? It is just, we need to solve this system. Here we have 1, 2, 0, right? And here we have 3, 2, minus 1. And here we have, what is it on the right hand side? 0 and 0. And which is 1, 2, 0, 0, multiplied by -3 and added to the second row. Here we have 0 and -3, -6 plus 2, -4. It is just -1 and 0. Or that is 1 and divide by 4. Here we have 2, 0, 0, 0, 1, 1 over 4 and 0, right? And multiply by -2 and add here 1, 0. So here we have -1 over 2, 0, 0, 1, 1 over 4, 0. So here we have a, here we have c, right? What we have here? A minus 1 over 2, c is equal to 0. And here we have b plus 1 over 4, c, that's equal to 0. Now from here, actually, they are just multiples of these two things. If I just take this c as 4, for example, and what we have here, that b will be -1, and a will be 2, right? So this will give us, what is it? The equation of the plane that passes through the origin. And this 1 to 0 and 3 to -1, they serve as direction vectors of this plane. All right, let's talk about these two things and I'll finish the class. That much is enough for today, I think. So we have two concepts here, linear dependence and linear independence. How do you define this linear dependence? So a set of vectors v1, v2, and vk. So we are given a bunch of vectors here, and we say that they are linearly dependent if there are scalars c1, c2, ck, and at least one of which is not equal to 0, such that c1, v1 plus c2, v2, simply the linear combination is equal to 0. If it is so, then we say that these vectors are linearly dependent. So what's going on here? As you see here, we are given k vectors, v1, v2, vk, right? And with non-trivial vector, right? Here we have c1, c2, ck, and non-trivial means at least one of these values is not equal to 0. So actually the linear combination gives us 0 vector. A set of vectors that is not linearly dependent is called linearly independent. That means that the only way to write the linear combination of these vectors and is equal to 0 is when all of the c1, c2, ck, these are equal to 0. Then we call them, they are linearly independent. Now actually this theorem actually gives us better picture of this. So vectors v1, v2, vm are linearly dependent if and only if at least one of the vectors can be expressed as a linear combination of the others. So that means that actually dependent means here we have, for example, at least one vector. Let's say this one v1. I can express this as a linear combination of the others. Okay, that means that this vector is dependent on this vector. It's not an independent vector. So we will see them in examples. Are the following vectors linearly independent or dependent? So that means that is it possible to find for A, for example, C1, and here we have 3, 1, plus C2, and here we have 1 minus 2, plus C3, and here we have 1, 11. So that is equal to 0 vector, 0, 0. Right? Can we find such numbers C1, C2, C3, at least one of them is not equal to 0, so that the linear combination, linear combination of these vectors, right, is equal to 0 vector. If so, that means that these vectors are linearly dependent. Otherwise, if the only solution of this system, as is a system, is only 0 vector, that means that C1, C2, C3 is equal to 0, that means that these vectors are linearly independent vectors, right? So to do so, what we have here, as you see here, to solve this equation, here we have C1, 3 times C1, plus C2 plus C3 is equal to 0. And here we have C1 okay. So C1 times 1 C1, C2 times negative 2 minus C2, and C3 times 11 plus 11 C3, that's equal to 0. And actually, we know that we are sure that if you remember from the previous session, right? And we are given a system of equations, and that is homogeneous. And how many variables we have here? Number of variables, 3. C1, C2, C3. How many equations we have here? 2 equations. That means that number of variables, that is equal to 3. And number of equations, that's equal to 2. We know that if is m equals 3, that's greater than 2. That means that here we will have at least one independent variable. So that means that it has infinitely many solutions. We can show this. So that means that these three vectors are, let's say this one is vector u1, vector u2, vector u3. So u1, u2, u3, these are linearly dependent vectors. All right. Okay. Well, let's have break for 1 minute. All right, maybe 2 minutes. After 2 minutes, we will continue. Okay. We have needed more space. Okay. How about for question B? The same thing. Is it's actually possible to find 3 numbers, let's say A, B, C, these are real numbers, right? So that when we just multiply this, linear combination of these 3 vectors, 1, negative 2, 0, plus B, and here we have 4, 0, 8, plus C, here we have 3, negative 1, 5. So here we have 0 vector. So if we can find non-trivial numbers, right? This A, B, C, not all of them are 0 at the same time. If it is so, then these 3 vectors will be linearly dependent. Otherwise, if the only solution of the system is 0, 0, 0, then it is, what is it? These vectors are linearly independent. To do so, immediately we know how to solve this system. We need to write the augmented matrix here. The first column is 1, negative 2, 0. 1, negative 2, 0. Second one is 4, 0, 8. Third one is 3, negative 1, and 5. And here we have 0, 0, 0. But anyway, let's just write this. Okay. So now here multiply the first row by 2 and add to the second row. Here we have 1, 4, 3, 0. 2 plus negative 2, 0. Here we have 8 plus 0, it is 8. And 6 plus minus 5, it is 5. So here we have 0. And here we have 0, 8, 5, 0. As see here, the second and third rows are exactly the same. If you just multiply the second row by negative 1 and add to the third row is equal to 0. And Here we have 1, 4, 3, 0, 0, and multiply the second row by, let's say this 1 over 8. So here we have 1, 5 over 8, 0, 0, 0, 0, right? And I can just multiply the second row by negative 4 and add to the first row. Here we will have 0 minus 4 times this is minus 5 over 2 and add to 3. So here we will have 1 over 2. 1 over 2. So that means that here a plus 1 over 2c, that's equal to 0. And from the second one, b plus 5 over 8c, that's equal to 0. Right? If I just take this c as, let's say, 8t, what we have here, this a will be 8t, it is 40 minus 40. B will be, it is 8 minus 5t. Right? And how many solutions does the system have? It has infinitely many solutions, right? If t equals 1, we have one solution. If t equals 10, another solution. So that means that in infinitely different ways, actually, I can just write as a linear combination of these three vectors where the linear combination is equal to 0 vector. So that means that these three vectors are, what is it? Linearly dependent vectors. Okay, these are linearly dependent vectors. Okay, and C, you can actually do it yourself. Let me skip this for you. So vectors v1, v2, and vm are linearly dependent if and only if at least one of the vectors can be expressed as a linear combination of the others. If you just show that actually one of the vectors can be expressed as a linear combination of others, and we can just say that, okay, then these vectors are linearly, or is it dependent vectors. Okay, any set of vectors containing the 0 vector is linearly dependent. Any set of vectors containing the 0 vector is linearly dependent. Why is it so? It's actually, if we have a set of vectors, let's say v1, v2, dot, let's say vk, and also actually it contains 1 0 vector. So the question is, can I just find, here we have C1 and C2, and here we have CK, one more CK plus 1, not all zeros, right? At least one of these is not equal to 0, right? From the definition. So that the linear combination of this vector is equal to 0. So if I just choose this as like this, 0 times V1 plus 0 times V2 plus, and here we have 0 times vk, right? And plus here we have non-zero number. Let's say here we have c times 0 vector is always equal to 0 vector. Here c is not equal to 0, right? And that's why if you're talking about a set of vectors, and if this set contains at least a 0 vector, then these vectors are always, what is it, linearly dependent. Okay, determine whether the following sets of vectors are linearly dependent. And guys, I will just leave this for you. We have already done a few questions. And I will finish the class with this theorem. Actually, we have another theorem here. Okay, I will continue from here next time. Okay. So this theorem says that let V1, V2, and Vm, they're given m vectors from n-dimensional space, and these are column vectors. And let A be the n by m matrix, whose columns are these vectors, V1, V2, and Vm. So then V1, V2, this Vm, these vectors are linearly dependent if and only if the homogeneous linear system with augmented matrix has a non-trivial solution, right? This is what we did in the examples. See here in the previous example, for example, here, right? As you see here, we have non-trivial solution. If the system, right, with this augmented matrix, it has non-trivial solution, then the vectors are linearly dependent. Otherwise, they are linearly independent vectors. Okay. Thank you very much. That's enough for today. Okay, see you next week. And if we have more things to share with each other, we can actually exchange our messages through Telegram. Bye bye. See you next Tuesday.